Thank you so much for having me on this workshop. I'd like to share my progress on recent progress towards data-driven recognition. The dictionary definition of recognition is the identification of someone or something or person from previous encounters or knowledge. That is, recognition is recognition. It consists of step one, object identification, which compares new data to old data, and two, knowledge extraction from the old data. To accomplish data-driven recognition, where natural data tends to be long-tail distributed, we must address long-tailed classification and natural representation learning. And that's the focus of my today's talk. When we reflect upon recognition, we seem to be able to talk about categories in isolation. For example, when we refer to dog categories, we don't need to mention anything else. That is we can recognize the commonness, the common dogness in all these instances, regardless of the object instances or the view variations. The key to object categorization from this perspective becomes achieving invariance to variations along these two axes. While recognition answers the question, what is a category? In modeling recognition, we tend to formulate it as a classification problem that can be captured in a two-level classification tree. The leaf nodes are the image instances and the root nodes are the categories. The categories, the names don't really matter in this case. What matters is the connection patterns, which tell what instances are together, what instances should not be in the same categories. So what classification gives us is differences among categories, not the categories themselves. So classification in general is not equivalent to recognition. For example, categorizing dogs away from cats and fox may only tell us how their eyes and tails are different, but doesn't tell us what dogs are like. As we learn more and more classes, the discrimination among dogs and all the other classes, then the dogness emerges, semantics emerges. The challenge in data-driven recognition is to approach that goal most effectively from limited data and the limited classes. So natural data is open long-tail distributed, which means that the majority of the categories along this class spectrum are having only a few instances. And the challenge is that how to leverage the majority instances in the head classes and generalize discrimination from the small data. The open-ended recognition means that a model also needs to maintain sensitivity to novel instances. This could be at odds of the tail recognition, where it demands a robustness. Lastly, when we put so much focus on the tail end of the performance, we tend to forget how to discriminate the head classes. But the performance on the head classes is what matters most often in the real world. So these three problems, imbalanced classification deals with the lopsided size differences, few-shot learning deals with small data learning problem, open set recognition deals with out of distribution detection, they have been dealt with in isolation, and many methods have been proposed, but they assume different training and testing settings. So the real challenge in the open long tail recognition is to handle all of them at the same time. When we coined the term open long tail recognition in 2019, we proposed a method with two key components. One is visual memory, and the other is attention, visual attention. Consider a tail class instance. It will activate memory about based on its head feature, body feature, and the tail features. That provides a great augmentation to what can be activated directly in the feature space. We use the finite instances in this tail class to learn how to select these features to enhance this feature so that the best discrimination can be achieved on the training set. With the memory enhancer feature, we can access the totality of the data through the memory bank. We can characterize how far it is to the distribution, and a decision with respect to open and closed sets can be made. We achieved major improvement on these benchmarks. In particular, we have 2% increase on the 1 million fine-grained face recognition data set. We extended this memory and feature idea to domain adaptation. The traditional setting is closed world recognition based on labeled source data and unlabeled test data. For example, you collect data in the sunny weather, a model is trained, and you want to be able to apply to data collected in rainy weather or some other weather conditions. We consider a setting where the target contains not only a discrete set of categories, but it could be mixed, unknown, or continuous domains. That is, we don't have the domain tags anymore. We also want to evaluate the model directly on the open unknown domain without seeing any data. Our idea is to first disentangle the feature. We learn the feature that's most indicative of the class, and the rest that's indicative of the domain. That's our assumption. Once that is the domain feature is learned, we can calculate the distance of each instance to the source domain. And then we can recruit these instances from near to far in instance-wise domain curriculum, and adapt the domain, use memory enhanced feature where the direct feature is modified according to the domain indicator. Now, let's take a look at the closed world long tail recognition itself. There are two key issues. One is this imbalance of classification. Usually it's associated with the consequence of model trivialization. For example, in a binary head and tail classification problem, a simple model always predicts the head will have a high accuracy. The model doesn't need to learn anything. But that obscure a large issue. The imbalance classification is not a number game. It is more of a diversity and a coverage problem. When you have many instances, the model can develop invariance to the view variations and object instances, can learn how to generalize. When you only have few instances, the information is chipped away in both directions. So the generalization across instances or across view variations becomes impossible. Not only that, the second problem is that, from these three finite instances, the model might have no idea how to develop something regarding to the articulation of the dog movement. While with the other three set of the tail instances, the model might draw the wrong conclusion that the dogs dogs tend to be dark-skinned. So there's a lot more variation in the finite data you can get. And that causes model instability. So I liken closed long tail recognition to rare disease diagnosis problem. When a doctor renders an ambivalent decision on a disease, we would seek a second opinion. If their conclusions don't reach any consensus, we seek a third opinion. When the training backgrounds of these doctors vary greatly, the more confidence we will have in their consensus. We deliver a model just like that, except that we derive that this consensus decision model through a principled model bias and variance analysis angle. Model bias and variance is traditionally formulated for regression problems. For example, if we want to fit a line predicting y from x based on the data collected, the underlying model is the gray line. When we collect the data, the measurements may contain random noise. The first thing to notice is that no matter what training data we have, it's just a subset, snapshot of all the data possibly out there. Here, each box contains such a data set, and the red line is our fitted model to these points. If we dump all these individual data sets and the fitted red line models into the same plot, we can evaluate the prediction error. On any point, the prediction error depends on which red line we use, which depends on which training data we have. It turns out the expected prediction error can be decomposed into three terms. The first one is measurement noise. There's nothing we can do about it. The second term is the so-called model bias. That's a difference between the average line of this red line bundle and the ground truth. The last term is the model variance, which measures how much variation this red line bundle has with respect to its average. Model bias measures the model accuracy. Model variance measures the model stability. We can extend the same analysis to classification. By sampling subsets from the training data we have, we can evaluate how a long tail method compared to a baseline, the vanilla cross entropy loss, which simply collects individual losses over the training set, disregarding the distribution over the classes. The large, medium, small circles here indicate the head, body, and tail performances. We are only interested in the performance number, whether they are above or below the diagonal line, where the two methods are on par with each other. We pick a representative prior leading approach in long tail methods, LDAM. By design, a long tail method boosts the accuracy for the tail and the body, but usually not mentioned is that it loses performance on the head. Whereas our method, named RIDE, can boost performance across all the spectrum. Noticeably is the increase on the head performance. In terms of model bias, LDAM reduces bias primarily on tail and somewhat on the body. We can reduce bias further for these classes. In terms of model variance, LDAM, like all other long tail methods we have tested, invariably increase the variance on all the class spectrum, head, body, and the tail, which means that a long tail method may give you better performance on the tail classes, but it fluctuates more depending on the data you get. R-right is able to reduce the fluctuation to be less than the baselines. So how do we do it? To reduce the model variance, we use this well-known result. Model ensembles can reduce the variance. But our ensemble is different in that we share the same training data and the same backbone with independent classification heads. Each expert is required not only to have good classification performance, but also collectively they diversify more for instances coming from the tail end of the spectrum. Ensembles improve in terms of model stability, reducing variance, but it comes with a bigger computational overhead. In stage one, we train these independent, but with backbone shared experts with minimum overheads on independent classification heads. To reduce the runtime compute at the test time, we train a router that decides whether we need to seek another expert. We show that the head classes mostly need one expert, while tail classes often need 3 experts in a 3-expert ensemble. Our method achieves SOTA on all major benchmarks. It is also a universal add-on that boosts performance over different long tail methods, training schemes. Any questions so far? Okay. So natural data is open long tail distributed. Natural learning of vision in babies face exactly the same problem. Babies have no sense of semantic categories, only sense of instances she interacts with. And she has massive experiences with very few instances and rare experiences with many. So how can baby learn something that's useful for the downstream recognition without any supervision when in the daily interactions? For downstream classification, it really could be arbitrary. The classification tree can be arbitrary. So how do we learn something that's useful? One thing that we could do is to learn maximum discrimination among all the instances, which prevents feature to prematurely collapse, so that if in downstream the categorization caused this and that instance to be different, you won't be able to do that. So long as you keep that distinctions alive, you would be able to enable the downstream recognition. This idea has been captured in our earlier work on ImageNet. Instead of classifying image into 1,000 predefined classes, mapping into the output space of 1,000 dimensions, we classify the image into 1.2 million instance space, which it requires 0 annotations. So we turn the supervised learning problem into an unsupervised learning problem. The challenge is that the output space is significantly larger. The second step is turning into metric learning problem. Instead of seeking a representation in the 1.2 million space, we seek a lower dimensional hypersphere. And the intuition is to find a position for each instance on this hypersphere, and each instance try to find its location and pushing everybody away from it. So in a crammed space, something has to give. In the end, those that share more data similarity will tend to be close to each other. So the pipeline goes like this. You have an image, you go through feature mapping, you find the position on the hypersphere, and you compare to the prototype in the memory bank. And this is so-called a non-parametric instance level discrimination. You accomplish this instance-wise classification. And during training, no labels are needed. For the sake of benchmarking, we use a label set to retrieve labeled neighbors for the sake of classification. At the time, it was the first time for our feature learning representation to pull the performance away from the semi-supervised learning camp using proxy tasks such as colorization. And this has led to a wave of contrasting learning methods such as SimClear, MoCo, and etc. And they really flex their compute muscles with a very large compute, pushing up the benchmark numbers. But what I want to focus on today is that we have instance discrimination, but instance discrimination is not enough for recognition. The baby step towards categorization is the need to recognize two different instances that look similar, could be of the same kind. How do we do that? If we want to go promote feature learning towards eventual categorization, this is a must step. It's not only, this problem is not only faced by babies learning how to see, but it's also a practical problem in discriminative learning from natural data, which is long tail distributed, or there could be correlated instances we just don't have tags for. So our idea is the following. How do we discover two instances, xi and xj, are actually the same kind? By instance discrimination, xi will repel xj and everything else except xi prime, which is augmented version engineered by us from xi. We would like to use this artificial group of xi prime to discover that xi and j are in the same group. The key idea is how do we capture the similarity between xi and sj? If we look at the local groups, xi will attract xi's prime's local centroid, but repel everything else. xj, being similar to xi, it will also attract to the same group centroid and repel others. Because xi and xj have exactly the same attraction repulsion patterns, they will be mapped into the same location in the feature space. That's our idea. Schematically, given the instance xi, we generate two augmented versions. They go through an instance feature branch and perform contrastive learning. And we calculate a separate feature branch and conduct the local grouping in the mini batch, and then perform cross-level discrimination. We are contrasting the instance level feature with the local centroids in a so-called cross-level discrimination. We maintain the resolution of instances, but what is being discriminated against is blurry, is fuzzy. It captures this the similarity between different instances. We are able to achieve good performance on all the benchmarks, on high correlation, long tail, balanced data sets, on transfer learning, semi-supervised learning with a much smaller compute compared to others. So far, we have all these results are demonstrated on data sets with a central object of interest in the individual images. But the natural scenes contain mixture of objects, like here, we have pedestrians, curbs, trees, buildings, cars. We have extended the image-wise feature learning to pixel-wise feature learning. where we first group pixels into segments in the feature space. And then we can perform image-wise discrimination in terms of segment-wise discriminative learning. Given a collection of unlabeled images, we are able to find the feature, their pixel clustering, and output predicted segmentation. And not only that, we can discover fragment clusters from the data set where we have hairs, faces, and helmets, so on and so forth. These are the semantics without names. Our pixel-wise feature captures not only what object each pixel is part of, but also the visual context it is embedded into. For example, here we have a bike rider, a motorcyclist in a back view, and a parked motorcycle. Such contextual annotations are not available during training. Even if we are able to come up with such a contextual vocabulary, it will be hard to specify the list of these types ahead of time. Yet we are able to discover all these contexts in a purely data-driven manner. We have extended our work to a unified approach on weakly supervised segmentation with a single contrastive learning loss. Whether the weak supervision comes from core supervision in terms of image tags or bounding boxes, or in terms of sparse annotations such as points and scribbles, where traditionally these two camps are handled using class activation maps and condition random fields respectively. We show the state-of-art performance in each individual camp. And when the scribbles shrink their lengths to points, we can see the greatest gain over other leading approaches. Current work progress, we have extended to unsupervised hierarchical segmentation, where we can discover scenes and their components in the feature, the pixel-wise feature itself. With this work, we can discover the thousands words associated with the unlabeled picture. For example, these magenta are the ones contain horses. We can discover horse riders without any annotations. So to summarize, I discussed our recent progress on data-driven recognition in two aspects. One is long-tailed classification. We find that feature attention and visual memory can augment the data in novel ways. And with the model bias and variance perspective, we can design a shared ensemble approach that contains diverse experts, particularly for the long-tailed data. This is so far, this is the only approach that reduce model bias and variance on long-tailed classification. Secondly is on representation learning from natural data. We show that the instance discrimination is a good internal prior for learning, and instance similarity can be discovered discriminatively, significantly improving feature learning with a small compute. We show extensions to pixel-wise feature learning, and these result in unsupervised semantic segmentation and visual context retrieval. I thank all my collaborators, students, postdocs for the joint work, and thank you for listening.